a very quick recap of what I was saying, that you can so in, for example, between 2 and 4 dimensions, all of these models have second order phase transitions formally, and they're applicable to nature. Like n equal 1 describes the critical Ising model, n equal 2 the superfluid transition, the XY model. For n equal 3, we get the critical Heisenberg model, and so on. And then you can use this trick of introducing the it's fine. Okay. So then there was a question, why is it non-local, right? Well, when you just start expanding this exponential, you see the exponentiation of this non-local term. It's very clear. So this double integral sigma of x, sigma of y just multiplies the free field correlator of I squared field. Okay, and you know exactly what is the free field correlator of I squared, right? It's 1 over x to the 4 right, or just something dimension dependent. So you get basically this non-local propagator structure for the sigma field, and the 1 over n is now hidden in this 1 over square root of n interaction, right? And then when you do the Fourier transform back, you get the 2-point function, which is 1 over x minus y to the 4. And this tells you that the dimension of the field corresponding to sigma is always 2. Right? This is exactly what I had here, that the leading term is just 2. Right? Not 1 that you would get in the free theory, but just 2. And then you can basically use this technique to develop this. Yes. Okay. Right. You get so then the structure is always like this. So, for example, the phi field, this is the free field dimension, and then there is a series of 1 over n corrections, and these are analytically computable as a function of d. Right? Yes.
In the previous slide, there was no n. There was no factor of n.
Sorry. Yeah, it's a slightly. I rescaled things so that this 1 over root n sits here. Yeah, but if I scale it back to how I was doing it before, then there would be 1 over n here. Yeah, I just put this in the vertex instead of the propagator. Okay, so then this diagram, just the sort of self-energy diagram for the phi 2-point function will basically look like this. And then usually you need to introduce an extra little regulator, because if you don't, then it's all going to diverge. So and then when you follow this procedure, you get this amazing formula that this eta 1, the 1 over n correction, you get it as a function of d, right? You don't just get it in d equals 3. You can really do it in any d between 4 and 2 or even above 4. And then you can basically do double expansion where you both do 4 minus epsilon and 1 over n, and there are all sorts of cross checks between this procedure and the standard epsilon expansion. So this, for example, gets you this analytic result, and then you can specify this result to this coefficient to d equals 3 to get the answer that I was quoting before, which is 4 over 3 pi squared. Okay, so following this, you can actually do the following calculation. So, for example, at order 1 over n cubed, you get these transcendental numbers appearing. And then people often compute 2 types of quadratic operators, the singlet one and the traceless tensor. This is so S is just phi I, right? And T is phi I phi j minus 1 over n phi squared, delta ij phi squared. Right, so T is just the traceless tensor. Like, so T is equal to phi I phi j minus 1 over n delta ij phi squared. Okay, and you see that they have rather dramatically different properties at large n. Like this one does approach 1. It's only this one that approaches 2. So this one is very close to the free field kind of limit, while this one is not. Okay, and then, so how can you test these 1 over n expansions? This is a bit of formal trickery, right?
What would happen if you wouldn't subtract?
You wouldn't get a good representation of ON, right? Yeah. Yeah. No, you always sort these operators into, like S is just a singlet of ON. Then you have to have traceless polynomials. Like, I mean, you would just get that mixture of phi squared. Yeah, yeah.
There is a delta ij.
Yeah, yeah. Yeah, they will be mixing. But this T, as written, will not mix. So it's a good operator. And so I will not talk about Bootstrap, but I'll just mention that this thing exists, and it relies on abstract properties of conformal invariance of the theory. Now, as far as I know, it hasn't been proven that this fixed point of the Ising or ON model is conformally invariant. Has it been proven? Yes? Okay, it has been proven. Well, I mean, but it's been assumed all along that it's very likely to be not just scale invariant, but fully conformally invariant. And here is already several years old results. Basically, they started cranking up n. This is something, n is just a parameter in their computation. And I think for the first time, they were able to actually test these large n formula to good accuracy. You basically, so they get like these nice kinks, and the true theory sits at these kinks. So these are the Bootstrap error bars. By now they've been improved a lot. And this dashed curve is just the 1 over n line, right? This is the plot of delta S versus delta phi. And you see that these kinks for even starting like 8, they are very close to what the large n result is. And they approach here, this 1 over n expansion very, very nicely. But you see, indeed, as predicted by Wilson and Kogat, right around n equal 8, there is a difficulty with this using 1 over n expansion to any specific order. Right. So I think this is one of the inherent features of 1 over n expansion in these purely scalar models. Any questions? Or?
The solid lines are what?
Oh, these solid lines are Bootstrap bounds. Okay. Like they basically say that the allowed range of dimensions based on some, they call it the oracle, or that the true theory has to sit under this line. Like if you plot delta S versus delta phi, it has to sit under this line. And there is some kind of kink or break in this line where the actual theory always appears to sit.
And we don't know why?
But there is by now much better data. Instead of these kinks, they have islands. They've managed to turn these kinks into little islands surrounding these points. At least for Ising and O2. Yeah, they do have some islands. But then already here you can basically test that the 1 over n curve is in very good agreement with the position of these kinks for n starting around 8.
And the dots with the points of the error bars are for low n? What are those confused?
They're an anachronism. Yeah, by now these error bars are much smaller and they turned into islands. But yeah, it basically is a constraint on, yeah, I think this is just the numerical error bar from the Bootstrap that by now shrank a lot. But the main reason I'm showing this is because of this part of the curve. Like this part of the, yeah, this is just the 1 over n theoretical curve that you see. It fails to pass through these points for small n, but it passes head on through the correct values at starting around 8. Okay, so now what about fermionic models? And I think part of the reason I wanted to mention it is because so this large n technique also allows you to deal to some extent with irrelevant interactions or with non-renormalizable theories. And yeah, too bad David is not here. But so one of these models is this Gros-Neveu model, which was originally introduced in D equal 2, where it was renormalizable. So I'll display what this model is. So the model is essentially, you just take a bunch of Dirac fermions with a simple interaction, which is psi bar I, psi I all squared. So it's again what I call double trace interaction. That's the only option you have in these vector-like models. And then, so since the canonical dimension of psi field is equal to 1/2 in D equal 2, right? This is in D equal 2 renormalizable. And what Gros and Neveu did is they did the large n solution of this model in D equal 2. This model does pick up quantum corrections, right? It picks up a beta function and it exhibits some dynamical phenomena in the infrared. But then the moment you go slightly above 2 dimensions, then the infrared theory becomes conformal. You basically lose the mass gap and it becomes conformal. So in some ways it has similarities. So in 2 dimensions it has some similarity with 4-dimensional QCD because it exhibits asymptotic freedom. But in 2 plus epsilon dimensions it's already a nice conformal theory, even though it's non-renormalizable technically, because right. So how do you solve this theory? Yes. Oh, it's just the convention. It's yeah. It depends on whether you, since it's psi bar. I think both signs of G are in principle allowed because it's a fermionic theory. One of them is attractive and the other one is repulsive. Yeah, since this is a potential term, usually you would put a minus sign, and this is just how you write the kinetic term in this convention. It's a Euclidean convention. So. Okay. You may see different conventions in different papers. For example, usually if you work in Lorentzian signature, I usually put an I in front of the.
The construction with gamma 5 is redundant, so it's like another construction.
Oh, in
Gamma 3.
in D equal 2.
Yeah, it's redundant.
Yeah, in D equal 2. Yeah, I think. Yeah. Right. That's a different model, but yeah. If you take them, it's not redundant. You can add this, and then there is this special chirally symmetric phase when there is a special combination of them. But yeah, it's not necessary. I think in D equal 2, it's.
This requires a chiral symmetry.
Right. Yeah. Yeah, this has only Z2 chiral symmetry, but not continuous chiral symmetry. Okay, so one thing that you can do is you can do 2 plus epsilon expansion, where you basically take this This is the beta function exactly in 2 dimensions, and then you have this plus epsilon g term, and then you get a g star coupling, which is also of order epsilon. So again, you see this feature that g star is of order 1 over n, right? This is like a completely generic feature. And the whole story is pretty similar to if you've seen the ON sigma model, which is also non-renormalizable above 2 dimensions. The whole story is very reminiscent of that. And this is already, you're on a bit of a dangerous ground here because you're really studying non-renormalizable theory, right? Because even in 2 plus epsilon dimensions, psi bar psi squared is a slightly irrelevant operator. But then you can try to use the fact that it's slightly irrelevant to develop this other kind of epsilon expansion. And I guess in the lectures on TT bar, you don't have this small epsilon parameter. You have basically, it's irrelevant by a lot, so you have to rely on some other sort of symmetries of the theory to try to make sense out of this. But now let's try to apply let's just try to apply the 1 over n expansion blindly, okay, as if in basically exactly the same way as we applied it to the scalar ON model, right? Namely, you introduce this Hubbard-Stratonovich field, sigma, right, and just write the coupling sigma times O, except now O will be psi bar psi operator, right? And then you find the following thing. You can just blindly expand again and get a non-local term sigma of x, sigma of y times the 2-point function Ox, Oy. But now what you find is that for this Gross-Neveu model, this power of p squared dominates at high momenta and not at low momenta, okay? Namely, so let's, for example, think about, let's think about d equal 3 case, right? Then delta O is 2, right? Delta O is just the free dimension of, so if you take the operator O, which is equal to psi bar I psi I, right? Then delta O in d equals 3 is equal to just 2, right? So now you see here 2 minus 3 halves, so it's plus 1 half, right? So you basically see that this goes like absolute value p plus some constant. Then what you can do is you can say, let me just formally ignore this constant now at high momenta. So this, so the idea is that you get a kind of growing interaction strength toward the UV, and in the UV you just formally drop this term and use this theory. And in that sense, the 1 over n expansion gives you a tool to study non-renormalizable theory. And I think people appreciated this also early on. This was before my time, and I don't remember who did this first. Maybe David was one of the first people who mentioned this in his maybe Lazouche lectures.
The original paper.
Right. Maybe in the original paper. So then you can just proceed along these lines and develop the same type of formula for delta psi and delta psi bar psi and all sorts of other operators. Because you have exactly the same technique, right? You have this induced dynamics for the sigma field. You drop this sort of bare term and work with these pure power law theories and obtain some set of CFT formula. And this looks like an honest second order phase transition, right? What does it describe? I think there are some ideas from condensed matter physics now that it may describe some quantum critical behavior of some superconducting transitions and like in planar theories, 2 plus 1 dimensional theories. But I think it's fair to say that its physical relevance is only starting to be explored. But it looks like another set of second order phase transitions labeled by n. And for example, you get the formula, like Gracie was one of the first people to compute these 1 over n expansions of these anomalous dimensions, and you again get the d-dependent formula, and you can compare its 2 plus epsilon expansion with what I already showed. But what about 4 minus epsilon expansion? And here actually came a nice idea, which is already many years old too, and it goes by the name of Gross-Neveu-Yukawa model. So basically, the truth is that this theory with a non-renormalizable interaction has a nice UV completion in terms of a fully renormalizable theory in below 4 dimensions. And the way this works is you just basically write a multi-flavor Yukawa theory. So you have this, if you will, this Hubbard-Stratonovich field becomes like a regular quantum field near 4 dimensions with a regular kinetic term and the sigma to the 4 interaction. And it has a Yukawa coupling to the n flavors of Dirac fermions. I think this was first pointed out by Zinjusten, and he was the one who called it the GNY model, or Gross-Neveu-Yukawa model. Its connection with the Gross-Neveu model is that if you add the sigma squared term, if you just add the mass term, you perturb this fixed point by sigma squared, you will generate from here, you'll generate psi bar psi squared term. So basically, I don't have too much room to write here, but yeah. So there is this GNY model, and it sits between just a free field, right? So you just have like the UV theory. So there is some UV theory of psi I fields plus this sigma field plus just one scalar field. Then there is this interacting CFT, and finally there is the IR theory of just psi I fields plus small psi bar psi squared interaction. And this CFT kind of sits between these two free CFTs, right? You can flow from this theory to the CFT by turning on this Yukawa coupling and sigma to the 4 interaction, and from the CFT you would add the relevant operator sigma squared. This is the only operator that you can add. And then you flow to just the theory of free fermions in the infrared. The interesting thing is that in 3 dimensions, the psi bar psi term has it's odd under time reversal or parity. So under this T symmetry, you basically have psi bar psi going to minus psi bar psi and sigma going to minus sigma. This already forbids odd powers of sigma, like sigma and sigma cube, and it forbids a mass term for the fermion. So the only tuning you have to do to obtain this conformal field theory is you just have to tune the mass of sigma to 0. So it's a very respectable looking theory with a single tuning. And I think there has been some lattice work on this theory, but just in terms of 1 over n and these epsilon expansions, they're all meshing together and making a lot of sense. Right, so in this case, for example, if you look at the IR fixed point in 4 minus epsilon dimension, you see that this Yukawa coupling here will go like root epsilon over n, and the the phi 4 or sigma to the 4 coupling goes like epsilon over n. And so it has basically the same respectable status as the ON model. Like it's a fermionic model where you can use both 4 minus epsilon and 2 plus epsilon expansion to mesh together what goes on exactly in d equals 3, which is the case of physical interest. And who knows, maybe there will be a crisp experimental test of this theory. For the ON models, there are certainly crisp experimental tests. There is even this famous satellite experiment about the XY model, which is always quoted by Bootstrap people as, in fact, it looks like it's slightly off. There is some experimental error there, and the Bootstrap is helping to correct this experimental error, but this is potentially also discoverable experimentally. Another thing that's very interesting about this theory is what happens for small n. This is, of course, outside the large n limit, but there is a very minimal theory with just a single Majorana fermion in 3 dimensions, and this theory has so-called emergent supersymmetry. So besides the interest at large n, you get at the smallest possible n. N is just a 2-component Majorana fermion in d equals 3. And this theory, this actually what we showed in a paper, at least started showing in a paper a couple years ago. In 4 minus epsilon expansion, it has emergent supersymmetry, and this tends to continue to 3 dimensions. So it could be like one of these condensed matter models that actually is accidentally supersymmetric. So this is, if LHC does not discover supersymmetry, maybe it can be discovered this way in some strange metal or something like this. Okay, so I think I don't. Okay, so I think this is most of what I had to say about the physical side of the vector models. They have sort of a very respectable status in the condensed matter community, and definitely help understand some things, or at least some of the phenomena like show up nicely in the 1 over n expansion. But as I said, you have to be very cautious with applying large n quantitative results at small n. And one thing that, for example, that can happen is, this is another fermionic model, 3-dimensional QED, is that as you reduce n, there could be a kind of transition in behavior. So instead of a conformal phase, you can suddenly get a phase with broken chiral symmetry. And I think I will not talk about this, but this is still a very actively debated subject, for example. In this model, it definitely doesn't happen. But in QED3, maybe I should mention also what QED3 is. But I think it will be mentioned in QED3 is, so what's the logic of this GNY model? It's very simple. You just take a renormalizable 4-dimensional theory and push it to slightly lower dimension than 4, right? So this is obviously one of the textbook examples, just Yukawa model. Now you can do the same thing for QED, right? You take
Do you still need this?
what?
Screen.
I can raise it, but if it's too much hassle, since I'm close to done.
Maybe all lectures will pass the course.
So QED 3 coupled to NF Dirac fermion. That probably will figure to some extent in Nathi-Zyberg's talk also. But in fact, there seems to be some new wave of papers on this, this subject. So here the action is very simple. You just have integral d dx, right, minus 1 over 4e squared f mu nu, right, plus I psi bar j, right, d slash, or d mu gamma mu times psi j, right, where d mu is just d mu plus I a mu. So this is just an abelian theory, right? Right, so it's just a QED coupled to a bunch of flavors, right? So for this theory, you can also develop both 4 minus epsilon and 1 over NF expansion, right? This J runs from 1 to NF. And often, there are different conventions in the literature, but often in this convention, you just think of NF as the number. So each of these psi is a four-component Dirac fermion. Right. Then you know that in 4 dimensions, the beta function for E is positive, right? Yeah, and so the theory would be completely free if not for the fermions, but you again get some kind of beta E will be minus epsilon over 2E plus NF E cube. And you get some kind of E star fixed point which describes conformal behavior. Or you can take induced QED, namely you can induce the non-local term using the fermion loop. And this is usually what we mean by conformal QED. You get some kind of non-local action for A mu, which is of order NF, and then you use it to dress up fermion lines and get the 1 over NF expansion. Completely analogous to how I was using the Hubbard-Stratonovich field. Okay, and so here, basically for everyone agrees on the following, that for NF bigger than some n critical, the theory is conformal. Theory in D equals 3 is a CFT. And the only question is, what is n-critical, or is there n-critical? And actually, so both Zohar and I worked on this question from different directions a couple years ago, and since then there has been various gyrations in this field. Basically, it's a very difficult question to settle using any kind of expansion. So you need some non-perturbative tools to settle it. But I think early on people proposed that for like for NF smaller than 2 or something like that.
There's a rigorous bound. That's the only thing that's going on.
Yeah, upper bound. But yeah, but there is no lower bound. Yeah, there are good upper bounds, but for example, people started saying that n-critical can be just 0, right? And it could be, but we don't know. And there is a plausible scenario of what happens below n-critical, namely that there is chiral symmetry breaking. You basically develop a vacuum expectation value of psi bar psi operator. So for n less than n-critical, can have essentially what happens is that this SU2NF symmetry, there is some SU2NF symmetry of the CFT gets broken. And this is actually, amazingly enough, just in the last couple of weeks, there have been several new papers on this. And some people are now saying that that there really is uncritical. Again, something of order 2 or, but so maybe it's so there is certainly still life in even these vectorial theories, and one over NF expansions are very nice, but they don't let you settle these dynamical questions that can happen at small n. Now I will start moving on to, I mean, vectors are tensors too. They're just tensors with one index. So I'll start moving to tensors with 2 and 3 indices and talk about what might be the physics of them. Yes.
Do you have some interpretation of these vector theories at n equals infinity, like you do for, say, matrix models when you have a holographic dual like that?
Yeah, holographic dual. Very good point. So each of these. So another reason we like large n is because large n is a natural home for dual descriptions. And all these large n CFTs have ADS duals, and they're so-called higher spin ADS duals. Yeah, gives me an excuse to mention my paper. But yeah, basically, so one kind of philosophical point is that, so I started with these 3 types of large n limit. Right, so the vector large n limit, and then the corresponding thing is the so-called higher spin theory in ADS. So in particular, the simplest higher spin theory is in 4-dimensional ADS and was written down by Vasiliev in 1992. And it turns out that for example, the ON vector model is dual to the so-called minimal Vasiliev theory. And the correspondence is basically very simple. It turns out that this ON vector model, you can write nearly conserved currents of any even spin. For example, in the ON model, namely you can write, so the simplest one is just the stress energy tensor, right? T mu nu is schematically phi I plus some terms. And then the next one will be some J4, will be phi I d mu 1, d mu 4 phi I. And these are, so in the free theory, these are exactly conserved. But even in the interacting fixed point, they're approximately conserved. And then the corresponding theory should have massless gauge fields in ADS4. So for example, this one is dual to spin 4 gauge field in ADS4. And so on for 6, 8, up to infinity. And basically, there are these Vasiliev equations that allow you to understand the interactions of all these higher spin fields meshed together. They're a complicated set of equations, but some success has been obtained, in particular by Jombi and Yin, mapping the correlation functions of these currents with the bulk calculation in ADS4. So this is an example of CFT3 ADS4 duality, but it works in a rather different way from, for example, the n=4 super-Young-Mills, because here you really have to take into account an infinite set of degrees of freedom, but they're sort of under control because they're gauge fields. And actually, the Gross-Neveu model is another example where this works. You have to take a somewhat different version of Vasiliev theory. Like this one is for some fun. Yeah.
Tutorial today.
Yeah. Okay. So am I done with time?
Yes,
yeah. Okay. So just the final note. So this is like People call this the type A theory, just from the structure of Vasiliev equations. And then there is also the GN, this GN model that's dual to so-called type B. And even this conformal QED, you just have to massage things a little more, and that also has a dual description in terms of higher spin. So all these vectorial theories have a nice home at large N in terms of these theories. And the reason large N is important is because the Newton constant Gn in the bulk is always of order 1 over n. So the large N is needed to get a weakly coupled bulk theory. Without it, you would not get a weakly coupled theory. So all small n theories inherently have strongly coupled bulk descriptions. Okay, I think I'll stop here.